Hello auditors, this is OpenZeppelin's Ethernaut Privacy Challenge. You can see that this is the privacy contract, and in order to solve this challenge, basically we need to unlock this contract to beat the level. This challenge is very similar to OpenZeppelin's Ethernaut Vault challenge, where we play with the data structure and algorithm of Ethereum's storage. So over here we have this particular article that explains how the storage works in Solidity. So over here, we have this locating fixed size values, which perfectly explains and illustrates how storage works using Solidity. So this is a simple storage test contract that we have a few variables, A, B, and entry structure. We can just focus on these two variables, A and B. So for A is a 32-byte state variable, while B is a 2-element fixed size array. So for A, that's actually stored at slot 0, while B is stored at slot 1 and 2, which each slot takes 32 bytes. So this is a simple illustration, slot 0, 1 and 2. For 1 and 2, state variable B or the array is actually given 1 and 2. Moving on, I'm going to further illustrate how the slot works. So over here, we got 1 byte. And since this is just only 1 byte and each slot requires 32 bytes, there isn't a need to force in 32 bytes here, which will cause some error, which is not theoretically possible. Thus, the best way is to create a new slot and add 32 bytes here. The reason why this is structured in this way is because of Solidity developers wanting to save costs for the gas, and thus Solidity smart contract is developed in a way that each slot takes 32 bytes. Now, moving on, over here we got these particular variables. There's 3 variables that is actually lesser than 32 bytes, and consecutively both are lesser than 32 bytes. So over here, for slot 2, which is a flattening variable that takes 1 byte. And since the second or the consecutive variable is only 1 byte, thus over here will be added 1 byte. And then over here, this is 16 bytes, and since awkwardness is 16 bytes, we are able to add here, and thus this is actually 18 bytes. And now, the most important thing is that the next consecutive variable, which is private data, is 32 byte each. We are not able to forcefully add into this particular slot. Thus, over here, we will add 32 bytes here, and then 32 bytes here, and then 32 bytes here. So each 32 bytes is actually each element within the array, since this array takes in 3 elements. So for the first element is 0, and then 1, and then 2. This is how list works. Now, moving on to solving this particular challenge is actually very simple. I actually created a simple interface that show me whether if the contract is locked or not. And then we actually extract the function unlock, which takes in a key, which is 16 bytes of the last slot of data. And if it is true, the locked will become false, which means that this privacy contract is unlocked. So this challenge is actually quite simple. We just have to convert this last particular slot. This last particular slot over here to byte 16, and then we'll just pass it as a key, and we'll make this particular smart contract unlocked and successfully solve this challenge. Okay, let's move on to the Brownie script over here. You can see that over here we got this particular script, and we basically take the last slot, which is this bytes 32, the data of slot 2, and then over here just pass it here, and then we just convert it into 16 bytes and then pass it into unlocked, and thus unlocking our contract. And you can see that over here we have successfully solved this particular challenge.